This video is talking about the formal definitions of the limits. Limits is a very important concept in calculus. Now, the main definition says that for a function f defined in some open interval containing a, but it's not necessarily defined at a itself, we say that the limit exists for this function when x approaching a if it's equivalent to some number L. How we are going to show that? If given any number epsilon greater than 0, there is another number delta greater than 0 such that if the distance between a and x in the x-axis is going to be less than delta, that will guarantee for you that is the corresponding value of your function at this x is going to be within a distance from L on the y-axis is less than epsilon. Let us see what does it mean, all these definitions. It's just a matter of a distance. We've been talking about when the limit exists, that means when we are approaching a certain number on the x-axis. If the limit exists, that means the corresponding value of your function approaching certain value on the y-axis. Okay, let us see. If the number that we are approaching on the x-axis is called a. Now there is two ways or two possibilities to approach this number. Either we are approaching it from left or we are approaching it from right. Now in both cases we wanted that if we are close enough from this number and if the limit exists, then that means the value of your function is going to approach certain value on the y-axis. Now we didn't mention, or most of our talking about the limit, we didn't define what do we mean by close enough. Now in this formal definition we give a notation for this closeness, which is determined by the symbol delta. On the x-axis, if you are away from the a by constant of delta, that means your number x is going to be to the left or to the right of a, and it is going to be the distance between it and between a is going to be less than delta. So it is going to be in this interval between a minus delta and a plus delta. Let's assume that this is your number x. Now, we wanted to make sure that is, what about the corresponding values of your function at this point x? Is it going to be within a distance from L on the y-axis? If that is the case, then the limit exists and it's equivalent to L. Now you could see that the corresponding value, the value of your function at this point x, is going to be in the interval between L minus epsilon and L plus epsilon. So that means the distance between L and f of x is going to be less than epsilon. Okay, so we started with a point x, which is going to be within a distance from a on the x-axis is less than delta, and we ended up with a value of your function at this x is going to be within a distance from L is less than epsilon. That means that the limit exists and is equivalent to L. And that's not just like, for any points that is to the left of your point A. It could also work for any point to the right of your point A. In this case, then we could say that the limit exists and it's equivalent to L. Now we notice that sometimes the limit exists, but your function, even if your function is not defined at the point itself. That's why in the formal definition we said that is your function f defined on some open interval containing a, but not necessarily at a itself. Let's see how we are going to use these formal definitions of the limit to prove that the limit exists. Now, some of the questions that you could expect for this kind of theory is that he will give you some limit is equal to some number, and he will ask you to prove that or to show that the limit exists. So what is the required steps in order to prove that the limit exists? The steps to prove the limit exists are three general steps. The first one is that we need to define annotations for the distance, which we mean by epsilon and delta, that are used to measure the distance from L and A respectively on the y-axis and in the x-axis. And then after that, once we define these two symbols, we need to make some calculation to find an expression of delta in terms of epsilon for a given epsilon. And the last step is that we need a conclusion to conclude that the limit exists if all these three steps are guarantees and satisfied. In the given example, he's asking you to prove that the limit when x approaching 1 for the function x squared minus 1 divided by x minus 1 is equal to 2. The first step, we need to define the distance notations. So assume that for a given epsilon greater than 0, there is another number delta greater than 0, such that if we start for any point within a distance from 1 is less than delta, then that's guaranteed that the value of your function at this point is going to be within a distance from the 2 in the y-axis is less than epsilon. So this is your assumption, and this is the conclusion you're expecting to get. If you start from this assumption and you get to this conclusion, then you already prove that your limit exists. Now, if I give you what is epsilon, how to find delta in terms of given epsilon? We would hope that we started from our assumption to get to the conclusion that we are getting. But since that is most of the time is not easy to achieve, so we'll do some mathematical trick here. We will start from the conclusion and drive our way until we get to the assumption, and this is only works if all our steps we could work them backward, so they are reversible. If that is the case, then that's fine. We could start from the conclusion in this case. So we start, that is the value of your function is within a distance from 2 is less than epsilon. Now we factor the numerators of our expression. You will find that we have a cancellation of some factors, and that's only true for all x's which is equivalent to 1. So we are not cancelling a 0 factor. And then we left with x plus 1 minus 2, which is simplified to x minus 1 is less than epsilon. So that means if we started with a delta which is going to be less than or equivalent to epsilon and work our way backwards step by step, we could start from the assumption we could get to this conclusion. And that is, what does it mean? So for a given epsilon greater than 0, if we choose the delta to be less than or equivalent to epsilon, and if we start with this assumption and worked backward in the above calculations, and that will get us to this conclusion that the value of your functions at this point x is going to be within a distance on the y-axis from the 2 is less than epsilon, and that is will prove for us the limit. Let's see that is, are you interested to know what is the graph of this function is going to be? If you are, then have a look at the next slide. In this next slide you will find that your function is going to be defined for all real number except at 1, because your function is not going to be defined at. So even your function is not going to be defined at 1, but still the limit exists and it's equal to 2. So within any distance from the 1 with a length which is going to be less than delta, you will find that any x that you are going to choose here, the value of your function is going to be within a distance from the 2 which is going to be less than epsilon, which proves that the limit exists for this function when we are approaching the point x is equal to 1.